Hello friends, welcome to the video. Our today's topic is differential calculus. Here we'll discuss about differential calculus as the rate measure and it is represented as dy by dx. This differential calculus, this topic is very important while doing physics course. So we'll try to learn it nicely. Now let's start. Consider there are two quantities y and x, and let the two quantities y and x are interrelated with each other in such a way that for each value of x there is one and only one value of y. This means for each value of x there is one and only one value of y, and this is the condition for being function. Now there is xy plane and there is one curve in this xy plane. Now for each value of x at each x, we will find the corresponding value of y with the help of height of the ordinate at that point. Suppose at this point, here the x coordinate is x, the value of y can be found with the help of the height of the ordinate from a to the x-axis at the point x. And the thing is written here, the value of y at particular x is obtained by the height of ordinate at that x. Now we are our main task here is to find how y is changing with respect to x. Now let us suppose, let x be changed by a small amount del x. Let x be changed by small amount del x, and let the corresponding change in the y be del y. If x is changed by the del x, then let the corresponding change in the y be del y. Now by as we think, or we can think, the rate of change of y with respect to x may be defined by finding del y by del x, or by finding the slope of this line AB, which will be given by del y by del x. And if this be the theta, the angle here, angle BACB theta, then we'll try to think that the rate of change of y with respect to x will be given by the slope of the line AB. And so I have written here, we can think the rate of change of y with respect to x can be given as del y by del x is equals to tan theta. But this expression or this equation is not the precise definition for finding the rate of change of y with respect to x in this curve, because if we apply del y by del x, then it will give the slope of this line AB. But as we can see in the interval AB, the curve itself is changing its rate. The curve itself is changing its rate at many places. At this interval itself is changing. That's why this could not be the perfect definition for finding the rate of change of y with respect to x for this curve. And I have written here, but this is not the precise definition of the rate. As we can see, the rate varies between the points A and B. The rate itself is varying from point A to B. Here the curve is more steeper at B than at A. The curve is not the straight line, so we cannot find the rate by using this equation. Now here, suppose we are focused on finding the rate at the point A. How we can see here, at each point of the x the rate is varying, because the curve is not the straight line, but it is not the straight line. That's why the rate itself is changing at every point in the curve. Now let us focus at a point here at A. Now we try to find the rate of change of y with respect to x at the point A. Now let us suppose, let's see here, let us make del x smaller and smaller. Let us make del x smaller and smaller. Whatever whatever small we make this del x, there will be the sum interval of this curve, or we will find this b will not coincide with a. That's why this del y by del x will not give the rate of change of y with respect to x. This will not give the rate as long as this del x is not made 0, and as long as this b do not coincide with a. This will not give the perfect rate of change of y with respect to x at a. That is written here. Let's see. Let us make del x smaller and smaller, but whatever small we take del x, as long as it is not 0, the rate may vary within that small part of the curve. If we don't make the del x 0, then there will be the some part of the curve, and in that interval of the in that part the rate may be varying in the curve. And let's see here, if we go on drawing the point B closer to A, and every time we calculate del y by del x is equals to tan theta, if we make del x smaller and smaller, and if B comes closer to the A, closer and closer to the A, and every time if we calculate del y by del x is equals to tan theta, we will see that as del x is made smaller and smaller, the slope tan theta of the line approaches to the slope of the tangent at A. If this del x is made smaller and smaller, this B will try to come closer and closer to A, and if del x is tends to 0, then the B will coincide with A, and this line BA, this line BA, which this tan theta gives the slope of the line BA, will this line BA, as B tries to coincide at A when del x tends to 0, then this BA will be tangent. This line BA tries to be tangent at the A, and that's why at that point this will be smaller, the slope, the tan theta of the line AB approaches the slope of the tangent at A. This will be the tangent at A. This line will be the tangent at A, gives the rate of change of y with respect to x at A. This gives the rate of change of y with respect to x at A. Here this will be this tangent as del x tends to limit 0, del x tends to 0, then there will be the tangent at point A, and if we calculate the slope of that tangent at A, then this will give the rate of change of y with respect to x at the point A or at the point x. Let's see here, this slope of the tangent at A gives the rate of change of y with respect to x at A. This rate is denoted as dy by dx, and thus we can now actually define the rate of change at particular x as follows: dy by dx at particular x, that means the rate of change of y at particular rate of change of y with respect to x at particular x can be given as dy by dx is equals to del x tends to limit 0 del y by del x. This is nothing but this is the slope of the tangent at that point. Let's see here. Thus, the rate of change is given by the slope of the tangent drawn at that point. Now there are some points which are very important. Let's see here. If y increases with increase in x at a point, then dy by dx is positive. If with increase in x there will be the increase in y, then the slope of the tangent or the rate will be positive, or dy by dx there will be positive. And next is, if y decreases with increase in x, if x increases and y decreases, then at that point dy by dx or the rate of change of y with respect to x will be negative. Now let us take one example here. Here is one curve drawn in xy plane. XY plane. I have plotted several points in x-axis and several points in the y-axis. And in the curve there are 3 points A, B and C. And now here we are asked to, if we are asked to find the slope at A, B and C, or how y changes with respect to x at the point A, B and C, if we are asked those things, then we can find the slope at A, B and C to find the rate of change of y with respect to x at these points by finding the slope of the tangent. So that's why in these points I have drawn here the tangents. Now let us calculate the slope of these tangents to find the rate of change of y with respect to x at these particular points. Let's see here, slope at A is equals to tan theta. Here this slope at A, this means the slope of this tangent at A can be given as slope at A. This will be given by tan theta. Let the angle made by the tangent at A with x-axis be be theta. The slope will be given by tan theta. Here in this triangle, the tan theta will be calculated as del y-axis divided by del y divided by del x. Here del y is equals to 2 units and del x is equals to 2 units. That's why the slope is y. Therefore, rate of change of y with respect to x at the point A is 1. Again, slope at B will be given by the angle made by this tangent at A at B with x-axis. Here angle made by tangent is 0. That's why the slope will be 0, and hence the rate of change of y with respect to x will be 0 at the point B. Again, let's come to the point C. At point C, to find the rate of change we have to find the slope of the tangent at C. Here y is positive 2 unit, y is positive 2 unit, and x is in this direction negative 2 unit. That's why the slope is -1, and this slope is calculated as tan alpha. This alpha is the angle made by this tangent with x-axis, and that's why the slope at C is -1. Hence the rate of change of y with respect to x is -1 at the point C. That's why here the slope is positive. That's why as increase in x, the y is increasing at point y. At B, the slope is 0. At C, as x increases, the y decreases. That's why the rate is negative here. Now let us take next example. Let us suppose there be the square of the length L, and its area be denoted as by A. That's why we can write A is equals to L square. Area is equals to L square. Now our task here is to calculate how the area changes with respect to L. With respect to L, how the area changes. Rate of change of area with respect to area. If small change in the length is made, then how the area will change. Let's see here. Area is given as L square. Now if length is increased or changed by del L, then if length is changed by del L, then there will be the change in the area as del A. That's why we can write A plus del A is equals to L plus del L whole square, or here A is equals to L square, we substitute A as L square plus del A, and here we apply the formula of A plus B whole square. That's why we get L square plus 2 times L dot del L plus del L square. Here L square cancels each other, and that's why del A is equals to, from these two terms we can find we can bring out common del L, and bracket, inside the bracket 2L plus del L. If we bring del L in the left hand side, then we'll get del A by del L is equals to 2L plus del L. Now we can find the actual rate by limiting del L to 0. That's why del L tends to limit 0. Del A divided by del L is equals to 2L, and here we put del L to be 0, and that's why we'll find this expression gives dA by dL is equals to L. This means the rate of change of A with respect to length at particular length is given as 2L. Given derivatives of some frequently used functions, d by dx of x to the power n is equals to n x to the power n minus 1. d by dx of sin x is equals to cos x. d by dx of cos x is equals to minus sin x. d by dx of tan x is equals to sec square x. d by dx of cosec x is equals to minus cosec x dot cot x. d by dx of sec x is equals to sec x dot tan x. d by dx of cot x is equals to minus cosec square x. d by dx of ln x is equals to 1 by x. d by dx of e to the power x is equals to e to the power x. Now let us move to the new topic, maxima and minima. Let us suppose x and y are related as shown in the curve. Here the curve here is at the initial the curve is increasing, that means as x is increasing y also increasing, and after the point A here, let us suppose this point be A. After this point, as x increases, the y gradually decreases, and as it reaches to point this B corresponding to x2, after this point B, the x, as x increases, then y again starts to increase. Here this point A is corresponding to point x1, this B is corresponding to point x2. Here the value of y, we have already discussed, the value of y at x1 or at any x can be found by the help of height of the ordinate at that point. And here we can see in this graph, at the point x1 the value of y is maximum. Here at the point A, y is maximum, and at the point x2 the value of the value of y is minimum. Here y is minimum. This is called local maxima and this is called the local minimum. Here we can see at maximum and minimum the rate of change can be found by the slope of the tangent, and if we draw the tangent there, it will be parallel lines to the x-axis, and therefore at maximum or minimum dy by dx is equals to 0. And here just after the maximum point, if we take the derivative, then the derivative will be negative, because as x increases y decreases. That's why at the maximum point, if we take the second derivative, it will give the negative value, or it will be the less than 0, or the slope will be negative. That's why at maximum second derivative will give the negative value. Again at the minimum, just after the minimum, the slope will be positive, because as x increases y also increases. That's why at minimum, if we take the second derivative, it will give the positive value, or it will give the positive rate of change of y with respect to x. That's why at maximum or the minimum, dy by dx is equals to 0. At maximum, the rate of second derivative will be negative. At minimum, second derivative will be positive. Here at some cases, or many of the cases, we need to find the second derivative to specify whether the function is in maximum, at that point is maximum or minimum. The condition gives us the clue whether there will be the maximum or minimum. That's why finding dy by dx, the second derivative of function, can be omitted. Here let's take one example. The height reached by the upward thrown body near the earth's surface with the certain velocity u is found to be function of the time given as h is equals to ut minus half gt square. Here height of the upward thrown body can be given at particular time can be given as ut minus half gt square. Here g is the acceleration due to gravity, which is the constant, and find the time taken by the body to reach the maximum height. Here maximum height, we have to find the time taken by the body to reach the maximum height. Let us do the solution. Here h can be given as ut minus half gt square, and we have already seen we can think here the height will be reached will be maximum, there will not be minimum, and we also know that at maximum the derivative will be at maximum or the minimum, the derivative will be 0. That's why we'll take the first derivative with respect to time, the derivative of height with respect to time. dh by dt is equals to dy dt of the first term minus derivative of the second term with respect to time, because h is the function of time, height is the function of time. Or as we know, at maximum we have to find the time reached, time taken by body to reach the maximum height. We have to find the maximum height. At maximum height, ds by dt is equals to 0. Therefore, we put 0. Here we will get u minus half g and t square. Its derivative will be 2t. 2 to cancel, and or 0 is equals to u minus gt, or gt is equals to u. Therefore, on simplification, it will give time is equals to u over g. That's why time taken by the body to reach the maximum height is u over g.